Hi, everybody. Today, we are going to solve 9701, paper 42, March 2025. The first question says, silver is a metal in the D block of the periodic table. Silver can form compounds containing silver positive and silver positive 2 ions. Explain why silver is a transition metal. So here we can say that silver is a transition metal as it forms variable oxidation states, or we can say that it forms at least one ion with partially filled d orbitals of d subshell. You can say both. Okay. The next question says table 1 gives data relevant to the Born-Haber cycle for silver 1 fluoride. They gave us the first ionization energy of silver. They gave us the enthalpy change of atomization of silver, the enthalpy change of atomization of fluorine, enthalpy change of formation of silver 1 fluoride, lattice energy of silver 1 fluoride. Now they said, write equations. So you see they want equations. Write equations for the standard enthalpy change described, include state symbols. So first they are asking us to write an equation about the standard enthalpy change of atomization of silver. And we know that the enthalpy change of atomization is the enthalpy change when 1 mole of an element in the gaseous state is formed from its element in its physical standard state. So here we have silver solid, which is the standard physical state of silver. It will form silver in the gas state. So this is the enthalpy change of atomization, where 1 mole of an element in the gas state is formed from its element in the standard physical state. The second equation, they said standard enthalpy change of formation of silver 1 fluoride. So we know that the standard enthalpy change of formation is the enthalpy change when 1 mole of a compound is formed from its elements in their standard physical states. So here we want to form silver fluoride solid from its elements, which are the silver solid, and here we have to put half fluorine gas because there should be here 1 mole of silver fluoride, and that's why we have to put here half fluorine gas. The next question says define lattice energy. We say that it is the energy released, or it is the enthalpy change, or we say it is the energy released when 1 mole of an ionic compound, when 1 mole of a solid ionic compound is formed from its ions in their gaseous states. So it is the enthalpy change, or it is the energy released when 1 mole of an ionic solid compound is formed from its ions in their gaseous states. Okay, right. Triple I says calculate the first electron affinity, EA1, of fluorine using the data in table 1 may be helpful to draw a labeled energy cycle as part of the working of your answer. So we know that here we have to draw the energy cycle, or if you can calculate the enthalpy change or the electron affinity without drawing the cycle, it's okay. But if we want to draw the cycle, we know that here we have to draw a line here and say that this is the silver fluoride solid. And then here we put a line and draw the elements of the silver and the fluoride. So here we have silver solid plus half fluorine gas, and by enthalpy change of formation, it will form the silver fluoride solid. And then we know that the silver solid will change into silver gas by the enthalpy change of atomization of silver, and the fluorine is the same. And then using the enthalpy change of atomization of fluorine is going to change to the fluorine atom in the gas state. And here we have the silver atom in the gas state. And then by the first ionization energy, it will form the silver ion plus electron, of course, in the gas state, plus electron, plus fluorine atom in the gas state. And then using the first electron affinity that they want us to calculate, we will get the silver ion gas plus the fluoride ion gas. And then by the lattice energy, by the enthalpy change of lattice energy, then we can get the silver fluoride solid. So we are going to see the values in the table. They said that the first, the enthalpy change of formation of silver 1 fluoride is minus 203. We have the enthalpy change of atomization of silver is positive 289 kilojoules per mole. The enthalpy change of atomization of fluorine is positive 79 kilojoules per mole. The first ionization is positive 732 kilojoules per mole. And the lattice energy is minus 955. So as we usually say that we have to find two roots. The first root is the enthalpy change of atomization. It's going on in this direction, but all the other arrows are going together, one after the other. So we say that minus 203 equal, we are going to take all the others together. So positive 289 plus 79 plus 732 plus x, we don't know what is x, which is the electron affinity. Then we have minus 955. And so we can get x, which is the electron affinity, the first electron affinity. So if we do this calculation, this means that we are having minus 203 minus 289 minus 79 minus 732 plus 955. So I got minus 348 kilojoules per mole. And of course, we have to get it in a negative value because we know that always the first electron affinity is a negative value. So it should be a negative value. Type number C says, use the data in table 1, 2 to calculate the enthalpy change of solution of silver fluoride. We know that the enthalpy change of solution is equal to the enthalpy change of hydration of positive ion plus the enthalpy change of hydration of the negative ion minus the lattice energy. So this means that we have, of course, silver fluoride. It ionizes to give silver ions plus fluoride ions, which means that we have the silver ion solid when it forms the silver ion aqueous plus the fluoride ion aqueous. We call this the enthalpy change of solution. And this is formed from the silver ion in the gas state plus the fluoride ion in the gas state by the enthalpy change of lattice. And we know that by the enthalpy change of hydration of both the silver ions in the gas state, the other way. So the silver ion in the gas state and the fluoride ion in the gas state, by the enthalpy change of hydration, they will form the silver ion aqueous and the fluoride ion aqueous. So here we see that the enthalpy change of the solution, as you see, plus the enthalpy change of lattice, together they will form the delta H naught of hydration for both the silver ion and the fluoride ion. And this means that the delta H of solution is equal to the enthalpy change of hydration of each of the silver ion and the fluoride ion, and then minus the enthalpy change of lattice. So here we have enthalpy change of hydration of the silver ion is minus 464, and that of the hydration of the fluoride ion is minus 506. And here we have minus and then minus 955. And so we will get minus 15 kilojoules per mole. And this means that when we get this negative value, this means that the silver fluoride can be soluble in water, because we know that when the delta H naught of solution is a negative value or a very small positive value, so this means that it is soluble in water. It can be soluble in water. So from here, it's obvious that the silver fluoride solid can dissolve in water. Now, they said, use your answer to CI, where we said that this is minus 15 kilojoules per mole. So they said, use your answer to CI to suggest whether silver fluoride is soluble in water at 298 Kelvin, and explain your answer. We say, yes, it is soluble. As delta H naught solution has a negative value. Okay. Let's see the next question. It says table 1.3 shows some data relevant to silver 1 highlights silver chloride to silver iodide. They gave us silver chloride, bromide, and iodide, and they wrote the first electron affinity of the halogen. It's for the chloride minus 349, for silver bromide minus 325, and for the silver iodide minus 295. The lattice energy minus 905, minus 890, minus 876. And they said, explain the trend in the first electron affinities of halogens, chlorine to iodine. So we see that the trend in the first electron affinity, it becomes less negative as we go down the group. And we know, of course, that the electron affinity means the ability of the atom to accept an electron, an incoming electron, to form the negative ion. And so we'll see that in case of the chloride, the radius is smaller than that in case of bromide, and this is much also smaller than that in case of the iodide. And we know that the incoming electron must be attracted to the positive nucleus of each of these atoms. So we see that as the radius increases, then the attraction force between the incoming electron and the positive nucleus of the atom will decrease. And so here they said, explain the trend in the first electron affinities of halogens, chlorine to iodine. So we say it becomes less negative from chlorine to iodine as the radius increases from chlorine to iodine, the radius increases. So the attraction force between the positive nucleus, or between the nucleus and the incoming electron, decreases. We can also here say as the radius increases and the shielding effect, also as the radius and shielding effect increases. As the radius, here we can say and shielding effect increases from chlorine to iodine, so the attraction force between the positive nucleus and the incoming electron decreases. The next question says, explain the trend in the lattice energies of silver 1 halides from silver chloride to silver iodide. So also we see that the lattice energies decreases or become less negative. The lattice energies become less negative, or we say decreases, as also the radius of the negative ion, or the radius of the halides increases. So less attraction. That's attraction force between the silver ion and the halide ion. We know that as the radii of both the positive ion and the negative ion are small. So this means that the attraction force will be big, but as we have the silver ion the same, but we have the negative ion increasing in radius or in size, and so the attraction force will be less. Here they said an electrochemical cell is constructed using the electrodes shown in table 1. Electrode 1, half equation, silver chloride plus electron gives silver solid plus chloride ion. The E naught is 0.222 volt. And for the second electrode, the copper plus 2 electrons gives copper. The E naught is positive 0.342. Calculate the standard cell potential E naught cell and construct an equation for the overall cell reaction. We know that always when we arrange the E naught values from the less positive to the more positive, so this means that the one that is the most positive means that its equation is going on the forward direction. It lies further to the right-hand side because it has a more positive value. And the other one is going to be flipped backward because it has the less positive value. And so we see that the E naught cell is equal to, we say, E right minus E left. The E right is the one that has the more positive charge, so positive 0.342, minus the E left, which is 0.222, And so for the E node cell, we get positive 0.12 volts. And when they want us to write the equation, so we are going to leave the equation of the copper as it is, and we flip the other equation. So the silver solid, so here we have aqueous plus 2 electrons gives copper solid, and here we have silver solid plus chloride ions give the silver chloride solid plus electron. And as we know that when we add these two half ionic equations, the number of electrons should be equal. And that's why here we have to multiply the second equation by 2 so that you get the same number of electrons to cancel. And the overall ionic equation will be copper 2 positive aqueous plus silver solid plus chloride ion aqueous gives silver chloride solid plus copper solid. So this will be the overall ionic equation. They said in a different experiment, electrode 1 is set up by using a saturated solution of potassium chloride. Saturated potassium chloride contains 36 grams of potassium chloride per 100 centimeter cube of solution at 298 Kelvin. The Nernst equation for the electrode 1 is E equal E naught plus 0.059 over Z log 1 over the chloride ion aqueous. Calculate the electrode potential E of electrode 1 under these conditions. Of course, as you see here, whenever we have a certain half ionic equation, this is when we say E naught, it means that it is present. This is the standard electrode potential. Standard means that it is obtained at standard conditions. But here, when they change to E, it means that now the concentration of the solution changed. The chloride ion concentration is not 1 mole per decimeter cube as it is required when we measure the standard electrode potential E naught. So E is the electrode potential at a certain concentration, and E naught is the standard electrode potential that is measured here, and this is the 0.22, and Z is the number of electrons involved in the reaction, and here we have the chloride ion. So here they are asking us to find out the E. And so we say that our equation is that the 2 chloride ions, they will lose electrons to form chlorine and 2 electrons. It means that here we have 2 electrons in our equation. So the Z is equal to 2. And now they said, let us see the first equation, electrode potential. So okay, but they are talking about electrode 1. So in electrode 1, we see that there is only 1 electron involved in the reaction. So this means that Z equal 1. And now we are going to substitute in the equation E equal E naught. So the E naught is 0.222 plus 0.0591 over 1 because the Z is 1 log 1 over the concentration of the chloride ion. So we have to get the concentration of the chloride ion first, and we can get it from this information that they dissolved 36 grams of potassium chloride per 100 centimeter cube. So here we are going to calculate the number of moles of the chloride ion or of the potassium chloride. We are going to calculate the number of moles of the potassium chloride, which is equal to the mass over the molar mass. So for the molar mass of potassium chloride, we have 39.1 plus 35.5. So we get it as 34.6 74.6. So this is 74.6. And here the mass, they give it to us as 36. And so we divide 36 by 74.6. So it's 0.4826. Do not make approximation until the end. And then this means that this is the same as the number of moles of the chloride. And here they said that the number of moles equal mass over molar mass, and we have to get the concentration. So we know that the number of moles equal concentration times volume, which means that the concentration equal the number of moles that we got here, divided by the volume, which is 100 over 1,000, because we have to change it into decimeter cube. So this is divided by 0.1. And we get 4.826 moles per decimeter cube. So this is the concentration of the potassium chloride, and it's also the concentration of the chloride ion, because we know that every mole of potassium chloride ionizes to give 1 mole of potassium ion and 1 mole of chloride ion. So this will be the same concentration of the chloride ion. So here we divide log 1 over 4.826. So we will divide log 1 over 4.826. So here we have a minus 683. So this times 0.0591. This will give us a minus 0.040. So here we have 0.222. And we get the E value to be positive. We have 0.181. 6, so it's 0.182 volts. So this will be the new E value. This is the electrode potential, the new electrode potential at the new concentration of the chloride ions. Now, in the second question, it says propanone, CH3, COCH3 is a common organic solvent and reagent. Propanone reacts with methanol under acidic conditions to form compound A, as shown by reaction 1. So in reaction 1, we have propanone reacting with methanol in acid conditions to produce compound A and water. The overall order of reaction 1 can be found by studying experimental data. Table 2 shows how the initial rate of reaction changes as the concentration of methanol and the concentration of hydrogen ions are varied. In each experiment, a large excess of propanone is used. They gave us 3 experiments. They gave us the concentrations of each of the methanol and the hydrogen ions and the relative initial rate of reaction. And in the first question, they said, explain why a large excess of propanone is used in each experiment. So we say that the large excess to make the concentration of propanone constant, so as to have no effect, on the rate of the reaction, So we say that a large excess of the propanone is used so that its concentration is considered constant, so that not to have any effect on the rate of the reaction. Then they said use the data in the table to determine the order of reaction 1 with respect to the methanol and hydrogen ions and explain your answer. So here we have to look at two experiments where we can have one of the methanol or the hydrogen ion concentration constant and the other varied, and see what is the relation between the concentration and the initial rate. So if we choose, for example, experiments 2 and 3, and we see that the concentration of the methanol is kept constant. So if we want to see what happened to the concentration of the hydrogen ions, so we divide 0.02 divided by 0.15 and see that the difference here is that we multiply the concentration by 1.333, and we see the effect of changing this on the rate. So we divide 3 by 2.25. So we see that also the rate here increased by 1.333. And this means that as the concentration, so we say that here in experiments 2 and 3, as the concentration of methanol is kept constant, and the concentration of hydrogen ions is multiplied by 1.333. The rate also is multiplied by 1.333, and this means that therefore the rate is first order with respect to the concentration of hydrogen ions. And then this is the first thing. And then we are going to choose any two other equations because we don't have a hydrogen ion concentration that is constant. So let us choose, for example, experiments 1 and 3. We'll see that the concentration here of the methanol increased by we see that it increased by 1.5. The concentration here increased by 1.5, and here it increased by 2, and here the rate increased by 3. So we know that it is first order with respect to the hydrogen ions. So as the hydrogen ions, as the rate is first order with respect to the hydrogen ions, so this means that if the concentration of the hydrogen ion increased by 2, this means that the rate should also increase by 2. So 2 times how much equals 3. So if we divide the 3 we get 1.5. So this means that here we have 1.5. And this means that if the concentration of methanol increased by 1.5, then the rate also increased by 1.5. And this means that it is also first order with respect to the methanol. So here we say that in experiments 1 and 3, as the concentration of hydrogen ion increases by 2, the concentration of the methanol increased by 2, the rate increased by 3. So this means that the rate is first order with respect to the concentration of the methanol as well. Okay. So now you know that it is first order with respect to the methanol and first order with respect to the hydrogen ions. They said in a separate experiment, a large excess of methanol and hydrogen ions are added to a solution containing a known concentration of propanone. So in figure 2 shows how the propanone concentration varies with time. Now they said use figure 2 to show how under these conditions reaction 1 is first order with respect to the propanone. So of course, we know that in order to prove that it is first order, we have to take the half-life times. And if the half-life times are equal or nearly equal, this means that it's first order. If we get a straight line, which we don't have here, then this means that it is zero order. But if the half-life times are double each other, this means that it is a second order. So to measure the half-life time here, we go from 100 to 50. And so we will draw a line from the 50 until we meet the curve here. And then go down. And we will see that the first half-life time is 170. So the first half-life time is 170 seconds. And if we go from 50 to 25, so here this is 20. So this is the 25. So if we go from the 25 until we meet the curve and then go down, this will be 330. This is 330, right? 1, 2, 3. So 330 minus the 170. So we get 160. So almost they are equal. And this means that here we have 160 seconds. So this means that it's also first order with respect to propanone. As the half-life times, and here we have to say that as the half-life times are equal, so this means that it is also first order, because they said under these conditions, reaction 1 is first order with respect to propanone. Show. So we have shown them, and we say that as the half-life times are equal, then this means that it is also first order. Now, they said here propanone also reacts with acidified cyanide ions to form the hydroxynitrile compound B, as shown in the reaction. In reaction 2, we have the propanone reacting with the cyanide in presence of an acid medium to produce the hydroxynitrile, which is the compound B. The following rate equation is determined for reaction 2. They found that the rate equal K times the concentration of propanone times the concentration of hydrogen ions. 4 possible mechanisms for reaction 2 are shown in table 2. They gave us 4 different mechanisms, and they said suggest which of these mechanisms is consistent with the rate equation for reaction 2 and explain your answer. So here we have to find one of these proposed mechanisms in which the concentration of the propanone and the concentration of the hydrogen ions, or I mean the propanone and the hydrogen ions, are present in the slow step, which is the rate determining step. We have to find in a slow step the propanone and the hydrogen ions present. So when we look at the first mechanism, the fast step, the propanone and hydrogen ions appeared in the fast step, not in the slow step, which means that we are not going to take this mechanism, because this mechanism says that if you react the propanone with the hydrogen ion to give this intermediate, and then this intermediate will react with the cyanide in a slow step to give the hydroxynitrile. So this means that the rate here is equal to K times the concentration of propanone times hydrogen ion times the cyanide, because all of them will appear in the rate equation, because the slow step was the reaction between the intermediate formed from propanone and H positive, and then with the cyanide. So this is not going to be the correct answer. If we look at the second one, we see also that in the first step, there is hydrogen ions and cyanide giving hydrogen cyanide, and then in the slow step, what is formed here, which is the hydrogen cyanide reacted with the propanone in the slow step, which means also here that the rate is going to be equal to the concentration of the propanone times the concentration of H positive times the concentration of the cyanide. Of course, we do not take the hydrogen cyanide because it's just an intermediate. So we have to right? The rate equals the concentration of all ions that appear or all species that appeared before the slow step and also included in the slow step. So this also is not correct. When we look at the third mechanism, we see that it is propanone and the cyanide ions that appeared at the slow step, which means that the rate here is equal to the concentration of the propanone times the concentration of the cyanide, which is not the case in our rate equation. So also this is incorrect. But when we look at number 4, we'll see that this is the correct mechanism because in the slow step appeared the propanone and the hydrogen ions that are present in the rate equation. So we say that the proposed reaction mechanism is reaction 4. And the explanation is that both the propanone and the hydrogen ions that are present in the rate equation are present in the slow step. The slow step includes the species that are present in the rate equation. So we say that in the slow step, the slow step includes the species that are present in the rate equation. Now they said that carboxylic acid C, so we have here B, which was the hydroxy nitrile. So this was B. Now they said that here carboxylic acid C4C, C4H8O3 forms when B is hydrolyzed under hot acidic conditions. Draw the structure of C. We know, of course, that when the nitrile group is hydrolyzed, and this is the nitrile group, it should be C triple bond N. And so when it is hydrolyzed, this bond breaks and this part changes to the carboxylic group, and this part changed to the NH4 positive. So they said, draw the structure of C. So it will be the carbon bonded to the OH, nothing changed. And here we have the COOH, and here we have the CH3, and here we have the other CH3. So this is the structure of C. They said that the pKa of C is 3.95. Calculate the pH of a 0.5 mole per decimeter cube solution of C and show you working. We know that the Ka for weak acids, Ka is equal to the concentration of the hydrogen ion times the concentration of the negative ion, which is the rest of the carboxylic acid, divided by the concentration of the acid itself, which means that we can say that here as the hydrogen ion and the negative ion are in the same mole ratio 1:1. So this means that we can remove the concentration of the halide negative ion, and we write H positive. So let us write it A minus, not to be confused. So here we have A minus. Whenever you have a weak acid, it ionizes partially to form the hydrogen ions plus the A minus. And here we have the acid dissociation constant, Ka, and we say that the Ka equal the concentration of H positive times the concentration of the A minus divided by the concentration of the acid HA. And as these two are in the mole ratio 1:1, it means that we can remove the concentration of the A minus and we write H positive squared divided by the concentration of the acid. And this means that the concentration of the hydrogen ions is equal to the square root of Ka times the concentration of the acid. And so it is equal to the square root of, we have to get back the Ka. So as the pKa is equal to 3.95, then the Ka is equal to 10 to the power minus 3.95. So I got 1.1 2 times 10 to the power minus 4 So this is the value of Ka. So we are going to multiply 1.122 times 10 to the power minus 4 times the concentration of the acid, which is 0.5. And so I got 7.49 times 10 to the power minus 3. And the pH will be minus log this value. The pH is minus log this value. And I got the pH equal to 0.133. So 2.13. Okay. Let's go to number D. It says C can be used to form a buffer solution D. Define a buffer solution. We say that it is a solution. Either we say that resists the change in pH, or we say that whose pH does not change significantly when a small amount of an acid or a base is added. So we say it is the solution that resists the change in pH, or else we can say it is a solution whose pH does not change significantly. We can say that it is a solution whose pH does not change significantly on the addition of small amounts of an acid or a base. Type. They said that buffer solution D made when 20 centimeter cube buffer solution D is made when 20 centimeter cube of 1 mole per decimeter cube sodium hydroxide is added to 100 centimeter cube of a 0.5 mole per decimeter cube solution of C. The pKa of C is 3.95, and calculate the pH of the buffer solution D. Show your working. So as we said, that the first thing that we have to know is that the Ka value is equal to 10 to the power minus 3.95. So here we get and so we got it before to be 1.122 times 10 to the power minus 4. So this is what we got before. And now we know that if they reacted the sodium hydroxide with the weak acid, which is the solution C. So if you have a weak acid and it reacts with sodium hydroxide, we know that the buffer consists of a weak acid and one of its salts. So the sodium hydroxide is not the salt of the weak acid, but when the sodium hydroxide reacts with the weak acid, it will form the sodium salt of the weak acid, and water is formed. So if we know the number of moles of sodium hydroxide, and as it is reacting in a mole ratio of 1 to 1 to 1 of the salt, so if we know the number of moles of the sodium hydroxide, we can determine the number of moles of the salt, and also we can determine how many moles of the acid reacted with it and how many moles of the acid remained in the form of the weak acid. And so when we have the weak acid and the salt number of moles, we can determine their concentrations and substitute to get the value of the pH of this buffer solution. So also here, we are going to first calculate the number of moles of the sodium hydroxide, which is equal to 20 over 1,000 times 1. And this means that we have 0.02 moles. And we calculate the number of moles of the acid C, which is equal to 100 over 1,000 times 0.5. So this means that we have 0.05 moles of the acid C at the beginning. And when it reacted with the sodium hydroxide, then part of this 0.05 reacted with the sodium hydroxide. And since it is reacting in the mole ratio of 1 to 1, so this means that the number of moles of C that reacted with the sodium hydroxide is equal to 0.05 minus 0.02, and this means that it is 0.03. This is the one that that did not react. The one that reacted with the sodium hydroxide, so the number of moles of the acid that reacted with the sodium hydroxide is the same as the number of moles of the sodium hydroxide, which is 0.02. And this means that the number of moles of C left in the form of acid is equal to 0.05 minus the 0.02, and we get the 0.03 moles for the acid. So since the mole ratio here is 1 to 1, this means that 0.02 moles of the sodium hydroxide reacted with 0.02 moles from the acid, and what will be left from the acid will be the 0.03. And for the number of moles of the salt, it will be equal to the number of moles of the sodium hydroxide will be 0.02, exactly right, like the number of moles of the sodium hydroxide. Now we want to get the concentrations, because we know that when a solution is added to another solution, the volume will change and the concentration will change. Yani, although we started with 0.5 mole per decimeter cube of solution C, in order to get the new concentration, we have to divide the number of moles we got by the total volume of the solution. So here we got the number of moles of the acid C that is left in the form of an acid, and this is the number of moles of the salt that is formed. So we are going to get the concentration of the acid C that is still present in the form of an acid. It's equal to its number of moles divided by the total volume, which is 20 plus 100 over it's 20 over 1,000 to get it in decimeter cube. And the concentration of the salt is going to be 0.02 divided by also 120 over 1,000. We can leave it as it is and canceling them together, or else we can calculate it. And so we have here 120 over 1,000 makes 0.12. So 0.03 divided by 0.12. So this will make 0.25. And for the other one, 0.02 divided by 0.12, this will make 0.01666. And so here we said that whenever we have a weak acid, the buffer solution, in the buffer we have the Ka is equal to the concentration of the H positive times the concentration of the A minus, which is the salt, divided by the concentration of the acid, which means that the hydrogen ion concentration is equal to the Ka that we got here as 1.122 times 10 to the power minus 4 times the concentration of the acid, which is the 0.25 divided by so Ka times the concentration of the acid divided by the A minus, which is 0.1666. So we get So I got 0.30, 168. And so to get the pH, it is equal to minus log this value that we got. So I got 3.7, 3.77. So this is the pH of the buffer. It is 3.77.